where do you download that? Is that Gibson?
Yeah.
No, it's not. Let's see. Yes.
Hello. So, the name shows this is the author, not me. Okay. So, I'm talking about simple online and real-time tracking with the deep association matrix. This is a paper, and it's also about multiple object tracking. It's same as the previous presentation. So what is MOT? What is multiple object tracking? So we can see a video. Okay.
Virtual box. You see. You want to pay the link? Wow. I guess too much advertisement. Well, this mouse is hard to use. It's better to stay outside. Oops. Why I cannot copy that? Hey, it doesn't work. Oh, I have lots of issues since I moved to 1604. Okay.
So for MOT, the popular solution is that we first extract all detections with detectors such as YOLO, fast CNN, and then we perform an association algorithm. This is the same as the previous Bernie's presentation, and the association algorithm is it usually consider motion information and appearance information. So it can, but sometimes or some people say that the motion information is not good if we have a lot of data. Compared to single object tracking, the MOT is harder because it has more problems, since in each moment the algorithm should decide whether a new track appears and whether a existing track disappears. So for this paper, It's an extension of a previous paper of simple online and real-time tracking, also called sort, and this paper is also called deep sort. So the motivation of sort is to explore how simple MOD can be and how well it can perform. And the motivation of deep sort is to reduce large number of identity switches in sort. So in other words, the sort performs bad sometimes. So deep sort is to solve the problems of sort. So as we said, we first extract all detections. Then we perform an extract association algorithm, which consider most of the information and appearance information. So in this paper, the detections are extracted using a detector, but it's not the key point of this paper. So let's talk about the key point. The how does this paper use motion information and appearance information? The motion information is modeled as 8 variables that each frame will show as the formula, where U and V is the bounding box center position, and gamma is aspect ratio. Is the gamma is the height divided the width, and the h is the height. So the first 4 variables contains all the geometry information about the bounding box, and the overdetermines their respective velocities in image coordinates. So these 8 variables should be updated every frame, and is updated with a common filter. So what is common filter? It's an algorithm that uses a series of measurements or observed data over time, and produce estimates of unknown variables or estimates of the next prediction. So if you are really interested in common filter, you can see a serious introduction on YouTube after this presentation. So the pipeline of MOT is that we need to, in this paper, we need to link new detections to existing tracks. So I think it makes sense simply. So if you have questions, you can tell to me. So when we link detections to existing tracks, we just simply calculate the distance of the grounding truth detection bounding box, and the common filter prediction is performed as this equation. So I think you don't need to really understand this equation, because it's just the key point here is that it calculates the cost of linking a detection to an existing track, and it uses the bounding box, the coordinates, to to do it. So there's also another kind of cost on motion information, which is IOU. It simply calculates the maximum overlap ratio of any bounding box in the track and the new detection bounding box. So this is very simple. So in this paper, besides of the cost, there's also a gate. So it's just a value to check whether it's feasible to accept this link. So in programming, it's a bool variable, bool. This value is got by a threshold. So that's motion information, and there's also appearance information. Appearance information is got by a convolutional neural network, and it's normalized to unite vector by L2 normalization, and we need to link a detection or detections to existing tracks. So we also need to compute the cost or the cost. The cost is simply calculated at the most cosine distance of the ith track and the jth detection. The ith track here in this paper, it only keeps the last 100 frames. I think it's for less disk storage, and similar to the motion information, there is also a gate variable. So the appearance information is very simple to explain here. So and we need to combine motion and appearance information. It's the same as the previous presentation. We simply use a weighted sum of motion information and appearance information, and then we got the final information or the cost, and we need to check whether the both information is should be accepted. So so this variable is just it's just combine the previous two gate variables. So if you don't understand this variable, it doesn't matter. So we can see the overall the whole pipeline now, and before that we need to understand the variables. So this is I think you guys can just see this. See the meanings of variables. Question?
Yes, I have.
Okay.
Can I answer?
Okay.
Okay. How about you to how to avoid I mean that if there is occlusion, how this algorithm can handle that?
You mean how to solve?
Yeah, how to solve occlusion if there is some of the that track is.
I know. I think the appearance information is used to track the problem of occlusion because it is invariant to occlusion, and you can see that here we keep the last 100 frames. So I think a pedestrian would not be occluded in 100 frames. So, and the cost of appearance information is calculated as the mean, the minimum, the minimum distance. Do you understand me?
What's the meaning of 100 description?
When we calculate the distance of the ice track and the J detection in appearance space, we for every frame in the ice track, we calculate its distance to the J detection, and then we select the minimum distance as our final distance.
Maybe some scheme of the operation. Maybe you can give example of video that there's occlusion inside that video and how the result using this.
Oh, okay. We can see the some results at the very end. But at first, I need to say that this paper is an extension of thought, and the motivation of thought is to explore how simple MOT can be, how simple. So it not treat the performance as its first goal. So
Do you think what the weakness of this algorithm? What the weakness is there? Are there the weakness of this algorithm that it is
weakness,
weakness?
the shortcoming drawback.
Yeah.
Okay. It has other drawbacks, and I will show it at a later time. I'll show it later. So we were talking about symbols in the pipeline. So let's talk about the pipeline. So at first we get the detection from another algorithm such as YOLO, factor ASEAN, or whatever, as long as it's a detector. And we compute the association cost matrix and the gate matrix as we talked before. And here we first in this for loop we select a track. We select a track, and n is the number of how many frames the track has not been updated. And then we select tracks, and we solve the assignment problem. So the drawback of this uh, method, as said in this paper, it has relatively more false positives compared to other methods, and the author said that there are two reasons. The first is the detector, but I think this is not a heavy problem because uh, detectors such as yellow fast arcane are very good, so it should be the problem of this method. The author says the second reason is the Emacs, where Emacs means checks has of how many frames track has no new added frames, so Emacs is set it as 30 in this paper. 30. Okay. So in practice, this method, I think is relatively much faster than other methods because with the detector it can have 14 FPS, a frame per second, 14 frames per second, and it's performed on a very large resolution video, and also it utilizes the GPU GTX 1080, and there's also public available code, so we can see some result. Okay. Sorry, let's see the result first. Okay. But I don't know how to. Oh, okay. I know. Yeah, there are a lot of fragments. Yeah, compared to other methods, it has relatively much more fragments. And
They don't have ID for all of this detected.
yeah, there's no ID, but you can see the color of the bounding box to
All
see.
the color is
Yeah.
ID.
Yeah, you can see so. Okay.
So you have a code for that? can try that with another video. Can you have that result?
Yeah, if you want to try, you can try. There's
And
Yes.
there's a result for it.
as showed here.
Oh,
There's a code with detector, so you can.
have you record the result and then can show up with you the result of the code that you type on yourself the video, another video.
No, I have no demo here.
Oh,
But the two videos we saw is coming from this method. Yeah. So
Yeah, I guess
let's show.
So, I'm not sure, like, it's so quiet in Norman. I'm not sure there's still anyone there. And I can't really see you guys, I guess. So, so anyway, like, remember that, like, to vote, not vote, but to rank the speakers, like, for today's presentations. I guess, so we just see you guys, like, next Thursday then. As I don't hear any questions, basically. Oh, there's still some people here. I'm so happy. Okay, thank you to be here. Okay, bye-bye. Yeah, see you guys. Oh, thank you.